my body's trying so hard to get sick. And I'm trying to not let it for another day or so. I call it the post-exam flu, because you're go, and then your body's like, oh, I'll just wait. But then as soon as you're finished, you get super, super sick. You'll see, it'll happen to you. It can happen to anyone. All right.
Are the marks posted online?
Yes, they are. Did I do the thing where you can see the distribution? I don't know. You tell me. I don't think so. But I'd say I'm pretty pleased with the test, how it went. I did think that I was kind of serving it up, but maybe you want more curveballs. I don't know. If it wasn't a good test, that's fine, right? As long as the final exam is better, then I'll move one of your tests to the final exam. So just have to keep improving, and that's all I want. That's all I can ask for. All right, so functions. Last day we did relations, which were things like, well, I guess we can go back there. Wait, that's the wrong section. Things like, well, I'm struggling because I can't really review a whole day's worth of material. It's a whole thing, right? But a relation can be something like this, right? Oops. So for my iPad's just so slow today. So for review, we talked about relations. I'll just paste them in here. Oh, yeah. Oh boy. There. Something like this, right? Where we said, just in general, if T is a relation, then 1 is related to 3, 1 is related to 5, 3 is related to 1, and so on and so forth. So we have some starting point, which is the first value, and then our second point is kind of the destination, so to speak. Okay? And so here we had this relation. Okay? Now functions are really just the special case of relations. Special case of relations. Yeah. Now, I do want to highlight that you have seen functions before in your previous math careers. Things like f of x equals, let's say, x squared. That's a function, right? And so what does it do? It takes an input, x, or I'll put it here actually, right? The input is x, and then the output is f of x. Probably seen some sort of function like that, right? Function notation, right? That's unfortunately not what we're going to be spending time on today. Bummer. it's the same idea, but we're gonna do it in terms of these kind of ordered pairs from the relations. Okay? And so there are rules around functions, okay? But the general idea is the same. We have some input value and it produces some output value. Okay? And then I tried to read this limerick, but I just can't get the, is it the cadence? A limerick, a countably infinite set is as simple as things like this get. Just start counting at 1, then continue. It's fun. I'll check back when you're done, so don't sweat. Hey, I nailed it. Ah, it's pretty good. Okay. A limerick. They're all limericks. Anyways. Now, for us, a function, it is going to be something like f of x is equal to x squared, of course, but we want to kind of get to the root of things. And so in that case, a function from a set A into a set B, so from some set of inputs to some set of outputs, okay, is a relation, so that's from last day, from A into B, such that each element of A is related to exactly one element of B. Okay? And the set A is called the domain of the function, and the set B is called the codomain. Okay? So what we usually do to visualize this is we have some set A and some set B. Nice. They should probably, they don't have to have the same shape, but kind of funny looking. So what it says is, in order to be a function, so a function that's taking, so a generic function f from a set A into a set B takes some point in f, okay, and it maps it to one element in B. Okay, so then we can have multiple values here. One element in A maps to some element in B. We are allowed to have something like this, where this value of y is not being mapped to. That's okay. But let's see if we introduce it here. Let me read this. A function from yeah. So we're not allowed to have something like this, where there's an element in A that's not being mapped to B. Okay, so this is not allowed. Then it's not a function. All right. Such that each element of A is related to, and then the exactly one element of the set B, right? You can't have something where this orange one, maybe it splits like this. That's not allowed either. Okay? We're going to come back to that, so I'll delete that for now. Okay? So, like I said, we are allowed to have unused values in B. Okay? However, we are allowed, let's see if I have, no, to have, I think of them as unused values, right? Unmapped to, that sounds weird. We are allowed to have unused values in B. So the set of values in A are called the domain, right? And especially if you think back to things like this, f of x is x squared, that's where we're used to working with functions, right? Something like that. Then the domain is all the values, all the possible values of x, right? And so that makes sense because that's the input. So that's our starting point. And so the values in the set A are the domain. Okay? The tricky one that we don't really talk about is the values. So the set of values in B, which is called the codomain. Okay? So here, the set A is called the domain of the function, and the set B is called the codomain. So if I draw my I'll write it on the side here. This is my domain, and this is my codomain. And there's a reason I'm not calling it the range. Oh, all right. Spoiler alert. Because the range is going to be the values. So it's always a subset of the codomain, but it's going to be the values that are actually mapped to, right? If you have one, a value in the codomain that's not included, right? It's not being mapped to, that's fine, that's allowed, but then it's not part of the range, right? Yeah. So in words, okay, and to clarify, because it's very important, each element in the set A, the domain of F, that's what we said. From here, my sideways written, must be related to some element of B, the codomain. Okay. So what does this mean? It means we can't have, can I call them unused? It's improper, but it's, I don't know. It works for my brain. I don't know about yours. We can't have unused points in A. Is what that's saying. And then is related to exactly one element of the set B means that you can only have A going to one output, right? So if AB is in the set of F, or in the function F, and AC is also in F, what does that mean? Well, the only way that that can happen is if B is equal to C, right? If they're the same point. Okay. Can I summarize that in a way? Each point in A can only map to one point in B. So if we consider this first example, and this is how we're going to be working with these functions is ordered pairs. And so get used to that. But that's also how we saw relations, right? And so we'll be used to it by then. So if we let A be the set of -2, -1, 0, 1, 2, okay, those are the values that I'm choosing from. And B is the set 0, 1, 2, 3, 4. That's my codomain, right? So my domain is -2, -1, 0, 1, 2. And my codomain is 0, 1, 2, 3, 4. And then if S is a function, and I'll just add a new page here, so I have some space for once, because I want to mark it up. Okay. Where are my? I need some lines. Doesn't want to give it to me. Okay, that's all right. Okay, so what does this look like if we draw out A? We're told that A has these values, and that's it. Okay. So let's jot those down. I'll start at the bottom because it feels weird not to. -2, -1, 0, 1, 2. Could have given myself a little bit more space, I guess. Make them dots. Why not? Hey, it looks like peas. Nice. Cute. S is a function that takes values from A into B. So here we just draw a little arrow. S is going this way. And B has possible values. I'll use a different color here. 0, 1, 2, 3, 4. I'll make them orange peas. Yeah. So what this function is saying, right? There's no math here. There's no formula that we're going to plug stuff into. It's totally back to basics, but in a weird way that somehow makes it harder. Or at least in my opinion. Okay, so S is going to take -2 and map it to 4. Well, I should have lined these up better. All right, so that's this guy here. It takes -1 from A and maps it into 1 in B. Let's see here. -1 maps to 1. Zero maps to 0. Running out of colors quickly here. 0 to 0. What are some things we're looking out for? There's 2 things that we need to look out for. I think we're told that this is a function, but let's confirm that it's a function because that's one of the things that we'll need to be able to do. And so that seems like a good thing to do then. What are the 2 things we have to look out for? We have to make sure that each element in A is being used, right? But also we have to make sure that one element in A can only map to one element in B, right? And so we'll keep going here, and they changed the, you can't even see me struggling to grab a different color here. No. There. How about decision paralysis? How about this? Very close to, that was a terrible choice. But 1 maps to 1. Whee. Feels like that's not allowed, but why is that allowed? We're allowed to have unique values of X going to the same value of Y, right? But I'm not allowed to have -1 go to 2 separate values in B. So now, oops, the last one is from 2 to 4. And let me just scoot this over just a switch here. S is a function because, right? And this is when we want to talk about all those or those two conditions, right? Because every element in A, right? Because one, every element in A is being used. No, is, you know what? I will say it. Is being used or is mapped to a value in B. And then the second condition was that one input can only produce one output, right? And so each element in A maps to only one element in B. Okay. Good. So being able to take a relation and recognize it as a function, right? That's going to be something that we have to do. Okay. And these two are the criteria that have to be satisfied. Okay. But if you draw them out, then you can pretty quickly see if it's a function or not, right? Or I guess with practice, but still. No, we don't need that. I'm going to focus on the ordered pairs. Yeah. And we've talked about the output, but sometimes we call it the image of a function, right? So I take some element in A and then I get the image, but they're all the same. I did want to highlight in here though, because this one, for some reason, I don't know, gut reaction. I just read it, the function f from A to B, and it kind of works. But you read it as let f be a function from the set A into the set B. Same deal. I think mine's just the sloppy version of that. The set, all that. Yeah. But what I want to talk about is the range of the function. Okay, so the range of the function is the set of images or the actual values that are being mapped to in B. Okay. I'll highlight this first. I went too far there. Okay. But the range, put it here. Notice that the range is different from the codomain. Right, the codomain was the list of elements in B, right? Which I think most of the time we would say is the range, right? But it's this kind of special relationship. So the range is different from the codomain, as not all values, or maybe I should take it the other way. I'll approach it from the other ways. So the range is different from the codomain, as the range is only the set of values being mapped to. From A. So going back to our generic, we've got A, we've got B. Every element in A has to map to some element in B, but we're also allowed to have an unused value, right? So all of these are the codomain, whereas these ones that are actually being used are the range. Where do I? So that's the difference. And then of course, these guys are the domain. But they're just always the domain, right? And we have to use all of them, otherwise it's not a function. Okay. As an exercise, let's just read this because it looks like gibberish, right? But if you just take it nice and slow, it's not too bad, okay? So if f is a function that maps from the set x into the set y, trying to be good about how I read it, then the range of f is this f of x, which makes sense from our original function notation, right? It's all the possible outputs, f of x. So then the range is going to be all the values from A, right, mapped onto B. Okay, so we have f of A is the output, or the mapping, I guess, where A is in X, right? So we're starting over here. So we have some generic A starting in, well, they're calling it X now, X and Y, but it's the same. I feel like maybe they copied and pasted from different notes somewhere. Who knows? So A is in the initial set, right, in the domain. And so f of A is the output, which is also the range, but that's the same as saying that there's some B in Y, right, which is the second grouping, right? So some B and B, for example. And then you read this as such that there exists an A in X such that f of A is equal to B, right? And so in order to get f of A, right, there has to be some, to go from A to f of A, well, then there has to be some B in Y. Man, they really mucked it up with the X's and the Y's. Okay. So like I said, functions, which we all know and love, probably, maybe, but make it harder, or harder to grasp intuitively, I think. Okay. What are they referring to here? Nope. I didn't highlight the exercises, but let's do these. I know, I usually put them off, but we need a little bit more practice before we can talk about other stuff. So if we're gonna let A be, and remember A is that first pod, let's think of it as the pod. So we've got A is 1, 2, 3, 4. Those are the only elements that we can have. And then B is the set of outputs, A, B, C, D. And then we want to determine which of the following are functions. And we have to explain, of course. And so now this is F is contained in the Cartesian product of A and B, right? But then we just define what F is anyways. So you can ignore that, I guess. But what do we want to do? We want to make sure that every element in A is being used, right? So we have to see a 1, 2, 3, and a 4, otherwise it's not a function, right? And every input can only go to one unique output. Okay? All right, let's do it. So first thing we check, right, is so 1, every element in A, is it used? 1, 2, 3, 4 looks good. 1, 2, 3, 4. Yes. I'll do A. X, or an element in A, go to only one element in B. In this case, 1 goes to A, and then I don't see 1 as an entry or an input again, so that's safe. Then I move on to 2, right? Same thing. I only see 2 once, I only see 3 once, and I only see 4 once. And so in this case, yes, which means that it's a function. Therefore, is a function. They're all relations, right? These are all relations. We can work with those. But in terms of a function, they have to satisfy these 2 criteria. So now, let's think about B. One goes to A, 2 goes to A, which feels weird, but it's allowed, right? What's not allowed? 1 going to A and then 1 going to B, that's not allowed, right? But we can have 1 going to A, 2 going to A, 3 going to B, and 4 going to D. So yes. And gonna be cheeky and just refer to these lists that I made earlier. And then elements in A go to only one element in B. Oh, whoa. I forgot to check. 1, 2, 3, 4 feels good. There, done. And then now I'm checking if they go to only one value. They do, because I only listed 1, 2, 3, 4 once. And so there can't be any duplicates. So yes, therefore it is a function. C is not a function. Think about why. Why? Nice. Because we're missing. So 1, no. 4 is missing. Therefore, it's not a function. Right? We've got inputs 1, 2, 3 covered, but then we also need 4, otherwise it's not a function. D is also not a function. Why? We've got 1, 2, 2, 3, 4. Uh-oh, I think I see the problem, right? And so, yeah, I listed all the elements of A, right? 1, 2, 3, 4, they're all listed. But here's the troublemaker, right? 2 is going to B and 2 is going to C, which we can't have. No, 2B and 2C can't be. Therefore, not a function. It can be in a relation, but it can't be in a function. Whoa. Kind of sneaky, but this is a function, right? I've got inputs 1, 2, 3, 4, so that's good. Right, yes. And then I just want to make sure, well, there's nothing I really have to check because I've only listed each input once. And so there's no risk of duplicate kind of tracks, if you think of them that way, right? And so here, it's just this super boring function. 1 is going to 1, 2 is going to 1, 3 is going to 1, 4 is going to 1. Sounds like a horizontal line at 1, right? Every output is 1. So it is a function, just a very boring one. Okay. Good. Next thing I want to do is add a page. Oh, sorry. I have to have a panicky moment, and I did record. Phew. Okay. So what I want to do is find the ranges of each of these relations that are functions. So we only find the range if it's a function. So we've already eliminated some of these because we decided, no, they're not functions. So let's go back and find the ones that are functions. The first one is a function. Copy. Paste. Uh-oh. I can just tell it's going to try to clunk out on me here. I can feel it. How about I grab all the ones that we decided were functions? A is a function, B is a function. C is not a function, D is not a function, E was a function. So the range is the set of outputs, right? Which is not necessarily the codomain. The codomain, notice, is the set A, B, C, D. So here, let me bump this down. Note the codomain is B, which was the set of A, B, C, D. Now the range has to be a subset of this, but not the entire codomain. So here, the range I'll just list them as a set. Well, now we just list the unique outputs. And so A, B, C, D, it happens to be the entire codomain, but it doesn't have to be. The next one, we only list unique values. And so I've got A, B, D. And so then the range is A, B, D. And then oh, caught me off guard. The 1 is not from B, but that's okay because it's in A by A. So it's going from A into A, but one's the domain, one's the codomain, and that's allowed. I missed it earlier, sorry. But it's that super boring one where the output's just 1 all the time. And so then the range is 1. All right. And here I'll just make a quick note. Note the codomain is the set 1, 2, 3, 4, because it's into A and not B anymore. Okay. Good. Okay. If we have A, 1, 2, 3, 4, and B, A, B, C, D, very basic starting point, and F is the function that takes from the set A into the set B and then now we're told that F of 1 is A, and F of 2 is B, F of 3 is C, and F of 4 is D, then we could rewrite this as a relation, right? This is the same as saying one maps to A, 2 maps to B, oops, too many commas, 3 maps to C, and 4 maps to D. So we could rework it to something that we're sort of familiar with, right? This relation style, ordered pairs. Same thing with this one. But now we have some input output scenario. Okay. Fine, let's do this one too. Oops, helps if I do it right. 1 maps to A, 2 maps to B, 3 maps to A, and 4 maps to B. Yeah, close enough. This doesn't really look like a D, does it? That's okay. Okay. So, both are functions, right? Every element in A is being accounted for, 1, 2, 3, 4. And although boring, right? Every element in A is only being listed once, and so then it has to have a unique output, and so it's a function, so both of them are functions. Now, what we're going to be talking about are one-to-one functions, which are, if you just had to guess what it is, might be something that, okay, looks like this. One input to one output, and it is. That's a one-to-one function. Okay. Satisfies the criteria. Every element in A has to be used, right? And to be one-to-one, a special case is that they only map to one output. We call it injective or injection. So it's injective if for all A, B in A, so every combo of inputs, as long as A is not equal to B, so they're two separate inputs, then that's the same as saying that f of A is not equal to f of B. They're going to separate outputs. Okay. So it's called an injection or an injective function or a one-to-one function. So it's one-to-one. If every input maps to a unique output. So that's where those peas in a pod just kind of help you visualize things, right? And so one-to-one, you've got this nice kind of shoelace looking thing. A function is surjective if the range f of A is equal to its codomain, which is really just saying that as long as there are no leftover values in B, right? So no values in B that are being unused. No unused values in B, then we say that it's an onto function. So we can think of them as surjective, injective. There's also bijective coming at you, but one-to-one, onto, I find makes a little bit more sense. Yeah. And so it's surjective or it's onto if an element of A, which they all have to be used, is going on to an element in B. So it's on to if each element in A maps onto one element in B where all elements are mapped to. I think the first part didn't really do the trick, Made sense in my head. Just trying to describe that there's none left over. They're all being hopped onto. So a bijective function is a one-to-one onto function. So it's both of those things, right? I guess we could have an onto function that looks, oh, no, not like that. Now I can't think of what to draw here. That's an onto function. It's not one-to-one, but it's onto, but not one-to-one. So one-to-one and onto looks like, well, one-to-one. And then maybe to emphasize, we could have an unused output in the one-to-one, but if it's one-to-one and onto, then we cannot. So if we have A is 1, 2, 3, and B is A, B, C, D, then what can we do? We could map these. We could write out the relations if we wanted to, but I think it might be easier to see if we just make our pods. So A has 1, 2, 3, and B has A, B, C, D. The function takes from 1 to B. From 2 to C. Whoa. From 3 to A. And that's it. It's a function because all these elements in A are being used and they're only going to one value in B, so that's all good. And now we want to know if it's one-to-one. Yes. Right. Every element in, it'd be nicer if I wrote the 3 up here, then they can just go across, right? And it would be, you'd untangle those a little bit, but every element in A is going to just one element in B, and it's a unique element in B. So it is one-to-one, but is it onto? And is it cake? No, right? Because D, no, D is not mapped onto. Right. That's okay in terms of being a function and stuff like that, but it just means that it's not an onto function. If a function is one-to-one and onto, then we've forced the scenario where we have all the elements in A, they have to be mapping to B, and they have to be mapping 1-to-1, which means I have to have exactly that many outputs, right? So as in A, but then if I also force it to be onto, then there can be none left over. And so then two sets are said to have the same cardinality, which is the same size, if there exists a bijection between them, which means they're 1-to-1 and onto. Which, if you know the definition of 1-to-1 and onto, then it just makes sense that they would have the same cardinality or the same size. Okay. Here, 1-to-1 and onto is the bijection. Because if you visualize it, A and B, if it has to be 1-to-1 and onto, you can't have any extras. And so A and B must be the same size. The cardinality of A must be equal to the cardinality of B. Countable sets. If a set is finite or has the same cardinality as the set of positive integers, which is infinite, right, in cardinality, in theory, you could keep counting, keep going, right? But so that's why we call it a countable set. But if a set has the same cardinality as a set of positive integers, we call it a countable set, even though it's not feasible. Right? And so what are we doing? It's kind of a fun way to think about it. If you have to count anything, right? Then technically, what are you doing? Taking a letter in the alphabet, for example, if you have to count that, then you're matching it, right, 1-to-1 with countable numbers, right? Positive integers, 1, 2, 3, all the way up to 26. You're finding that cardinality, and then you're assigning that to however many letters you have. So kind of a backwards way to think of it, I guess. Kind of fun. There's also a thing called the pigeonhole principle, which we use quite a bit in math. Okay, but so it is kind of lengthy like this, but if you have a room that has 4 students with the first name John, James, and Mary, okay, prove that 2 students have the same first name. Well, if there's 4 students but only 3 names, then, right, I have my students here, and I have my names here, right? Student 1, 2, 3, 4. Then 3 of these can be 1-to-1, right? 1, 2, 3. But by the pigeonhole principle, and so what it says is, well, it has to be forced in between here, right? Especially if you find upper and lower bounds on values, you can use the pigeonhole principle. Well, it has to be somewhere in here. And so this student name is going to be the same as one of the others because there's only 3 things to map to. Nice. Why not? Whoa. Whoa, whoa, whoa. Okay. I'm gonna go grab those functions that we already talked about, right? We figured out which ones were functions. We figured out what the ranges were of those functions, and now we're going to figure out which ones are one-to-one and which are onto. So please stay on the line. Or maybe I can just do this. Mm-hmm. Okay. I'd say the easiest way to determine if something is one-to-one and or onto is to draw the pods. Hey, it really doesn't want to work with me today. Or maybe I just don't want to work. That's an option too. Okay, so we've got our pods, A and F is going from A to B, and A was 1, 2, 3, 4. 1, 2, 3, 4, and B was A, B, C, D. 1 maps to A, 2 maps to B, 3 maps to C, and 4 maps to D. Nice. That looks like one-to-one to me. And also onto, right? Because there are no leftover values in B. So this is one-to-one and onto. Oh. Bump this down. How about the next one? So same deal. A, B, 1, 2, 3, 4, A, B, C, D. G is a function from A to B. And so 1 goes to A, 2 goes to A, 3 goes to B, and 4 goes to D. It's not one-to-one, right? And it's also not onto. So here, not one-to-one. And here it's not onto because C is missing. Right? One-to-one is when you have one input to one output and the output is not being reused. It's a function, but it's not a function. Now I'm going from A to A. 1, 2, 3, 4. 1, 2, 3, 4. It's function L. 1 is going to 1. 2 is going to 1. 3 is going to 1. And 4 is going to 1. Super boring. Definitely not one-to-one. And definitely not onto because it's missing all these guys. Not onto, that's for sure. And not one-to-one. Oh, I threw in another dash there. Mixed it up there. One-to-one. Good. Is there another one I wanted to do here? I don't think so. Notice how I'm skipping a lot of these. That's okay. Function compositions. If you've worked with functions, you've probably done function composition where you take one function and you stuff it into the other function as the input. Okay, so function composition is when you have things like f of g of x is function composition. And so g of x is the input into f of x, but g of x is the output of g at x, right? Out of one function and using it as the input in the other function. So if f is a function from the set A into the set B, and g is a function from the set B into the set C, then the composition of f followed by g, which we write as g as a composition of f, or you can read this little dot as of g of f. So g of f is technically g composed with f. Or g of f is how I read it. And it also kind of lends itself to that. And so what is g of f? Well, it's this g of f of x. So it goes from A into C, and the function is, you work it the exact same way that you read it. So g composed with f is g of f of x, which means that you have to find f of x and then put it into g. I want to put this one on a new page here. So f is a function going from 1, 2, 3 to AB. And the function says that if I have an input of 1, I get an output of A, right? And you can translate these to relations if you prefer. If I give it an input of 2, I get an output of A, and f of 3 is B. Then G is going to go from A, B to 5, 6, 7. And we're told that G of 5, or G of A is 5 and G of B is 7. Then G composed with F is going to bypass the middleman, I guess, and take from 1, 2, 3 and produce an output in 5, 6, 7. So G composed with F is the same as G of F of X. So if I want to find specifically G composed with F at 1, what does that look like? G composed with F at 1 is G of F at 1. Which means that the first thing I need to do is I need to find f of 1. F of 1 is A. So then what I want to find is G of A, which we're told is 5. So now it's a multi-step process, but as long as you go nice and slow, then you can map them back to each other. Let's see here. Let's find G composed with F at 2, which I always find it helpful to rewrite it in terms of just the function. So G of F of 2, because that's how we were given the information. So F of 2 is A. So G of A is 5 again. Did I get that right? Yeah. G composed with F at 3. Is G of F of 3. F of 3, we were told is B, so G of B we're given is 7. So not too bad. We can flip the order, F composed with G, but the outputs of G have to be inputs of F. Okay, and so let's try F composed with G at 1, for example. I think it didn't specify. G, okay, fine. Let's do G of, how about we do it at A instead? That's an input of G. So then we want F of G of A, which is the same as F of G of A was 5. F of 5 doesn't exist, right? And so we have F of 1, F of 2, and F of 3, but F of 5 doesn't work. Does not exist. Five is not in the domain of F. So sometimes it only works one way. If we have two functions, F, which is going from A to B, and G, which is going to B and C, and H, which is going from C to D, then you're allowed to link these guys up. Okay, so it's associative. Then you can say that H composed with G composed with F, as long as you're doing G composed with F first and then putting it into H, that's going to be the same as H composed with G, then composed with F, and the order matter, right? That's what a associative means. I want the ivity. It's not coming. But I feel like I scrolled past something. That's fine. Okay. Let's skip that. Just as a fun fact, a theorem, in fact, if I have the composition of an injection, 2 injections result in another injection, same thing. And what was the injection? Injection is 1 to 1. surjection is onto, right? So if you have two onto functions being composed with each other, then the result is also onto. Now we introduce the identity function, which is basically one, right? And so the identity function, we use a lowercase I in this case. Sometimes for matrices, we would use a capital I, but either way, I as a function on A just returns itself. So it's basically like, I think of it as multiplying by 1. It's not really what it's doing, but I'll put quotes around it because that's how I think of it. So the identity function, you can use it as a function, but it'll just return whatever you put into it. Okay. So if we have a function, then f composed with the identity is the same as the identity composed with f, which is not always the case, right? We saw that g composed with f is not the same as f composed with g, but with the identity it is, and it just returns the original function. So that's boring. But it leads us to the inverse function. So the inverse is the function that undoes the original function, right? And so it makes it work backwards. And so if I have a function where g composed with f is the same as f composed with g, but not just that, but wait, there's more, and it equals the identity function, then g is called the inverse of f, and we denote it by f to the negative 1, and we read it as f inverse. And so the inverse kind of undoes whatever f does. I won't copy this one, but the inverse of a function on 1, 2, 3. So if we have a function where f of 1 is 2, f of 2 is 3, and f of 3 is 1, then the inverse of this function, right, even without this here, would say that f inverse of 2 would give me 1, right? F inverse of 3 is going to give me 2, and f inverse of 1 is going to give me 3. Right, they've got them written in different order, but that's okay. Right, and so we just, it works, or it kind of reverses the input output. We said that if I can find a function where I compose it with another function and I get the identity, right, the identity function, then as long as it works for both variations, then I have the inverse. Wait. Now, the inverse exists if and only if f is a bijection. So only if it's 1-to-1 and onto. Has to be 1-to-1 for sure. Otherwise, it's going to be really hard to take an output and map it back to an input, which is what the inverse is doing, right? So if it's trying to go back to two different things and it doesn't know how, then it doesn't have an inverse. Right, and so here, if you have something like this, ding, 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 where this little guy and this little guy map to mapped to one value, that's allowed, that's a function, right? But then the inverse, no inverse exists, right? Because there's no way for us to know, okay, I have this output, is it going to go to this one or is it going to go to that one? Same thing here, this one doesn't have an input to match to, so that's also a problem. No input, right? So that's why it has to be one-to-one and onto in order for it to have an inverse, which is going this other way. F inverse. And I think I think that's all I want to do. I didn't really like these exercises that much. We could do one, I guess, but I'll make up some exercises that I like for Friday. How about that? How am I doing? Whatever. I'm losing my voice anyways. Any questions? Comments? Concerns? If you have any questions, let me know. Otherwise, we'll stop there. Functions. We'll do more examples on Friday. Until then, make sure you grab your test. Stop this recording.